Hi, my name is Mike. I'm a respiratory therapist, and today we're going to talk about the very basics of compliance and the basics of airway resistance. And then we're going to apply that to the mechanical ventilator, how we can use those concepts actually at the bedside. So first, let's talk about compliance. In its basic form, compliance is the amount of volume an elastic body like a balloon or the lung, how much volume that will accept per unit of pressure applied. So our most basic formula would be compliance is the volume accepted over the pressure it took. And so we can look at compliance. I have a balloon here and I'm going to blow it up. So there's a certain volume in there that I blew in there, and there's a certain pressure in there. So its compliance would be the mathematical formula with those two in there. Now, I don't know what pressure is in there, and I don't know what volume is in there, but just at its basic, people tend to get this because it's an example that everybody's familiar with. So if this lung or this balloon were stiffer, less compliant, less accepting of air, then it would take more pressure to get that same volume in there. Okay, all right, now let the air out of that balloon. And so let's put some numbers here. Let's talk about the lung. And so let's say that we are wanting to push 500 milliliters into this lung. And we're gonna say that we're targeting 500 milliliters. So on a ventilator, we can type in exactly what volume we want. It's a fixed number. And so we say, okay, ventilator, push this volume in there. And in this case, it's gonna be 500 milliliters. And then the ventilator is gonna use, within limits, what pressure it takes, depending on how compliant the lung is. So in this case, let's just say that it took 25 centimeters of water pressure. So this is volume and pressure, and we work that out mathematically, and none of these units cross out, so we're gonna just carry them through. And so we divide 500 by 25, and we're gonna get 20 milliliters per centimeter of water. Now let's think about that so it's not just a number. That means that for every one of these units of pressure, the lungs accepted 20 milliliters of gas. So let's say that something happened, the lung got stiffer, less compliant, there's fluid in there, atelectasis, pneumonia, maybe something in the pleural space around the lung like a pleural effusion, or some chest wall thing that happened. And so now we're still gonna push 500 in there, but now it's gonna take 30. And I'm just pulling that number, just to give it as an example. And now 30 centimeters of water it took. So let's think about that. Same volume took more pressure. If this were applied to that balloon I blew up, that means I would have to push harder, I'd have to blow harder in order to get that same volume in there because the balloon is stiffer, less compliant. And so we work this out mathematically and we get 16.6 milliliters per centimeter of water. And we can already see that the lung is less compliant, it's less expandable, it's less accepting of air. It's only taking 16.6 milliliters of gas for every unit of pressure, where over here it took 20. So that's kind of the very basics of compliance. And so let's talk about what makes that number, like what determines the compliance number. Well, when we push gas in there, there's a couple of concepts at play. There's resistance and compliance. We're just gonna isolate out compliance right now. So if we were to look at the lung, and I'm just gonna put a little bit of airways here and some gas exchange units, and it's kind of a rough drawing there. And then we have the pleural space around it, and then we have the chest wall. So when gas is in there, we have some forces that it has to push against to get the gas in there. And naturally, the lung is elastic, so it wants to naturally pull in. And we have, other forces that pull in, like water vapor in the alveoli and things like that. And then the rib cage wants to pull out, and actually not part of this talk, but that's what makes the negative pressure in the pleural space, because it's a sealed space. But anyway, there's three general areas that make compliance, that pressure. The first area is in the gas exchange units. So anything in there like fibrosis or fluid or pneumonia or collapse, trying to push gas in there, it's not going to accept air very well. And so it's going to take more pressure. Things in the pleural space, whether it's any kind of fluid of any kind, or blood or whatever that's in there, then that's going to make the lung less compliant. And then we have chest wall things. There's chest wall deformities, you know, kyphosis and scoliosis, and we have things on the outside, like if somebody is very overweight, we have, you know, all that body fat pushing down. The lung has to push open. You know, the ventilator's got to use pressure to push that open to raise all that. Other things, if somebody's burnt all the way around, burnt tissue doesn't really expand very well. So those are some examples. So the first area is the gas exchange, second area is the pleural space, third area is the chest wall. Now, we talked about the chest wall, but you also have to remember that the diaphragm is here and it's got to push down. So anything down here in this area below the diaphragm that's in the way of diaphragm movement, the ventilator is going to have to use pressure to open that lung to push against that. That can be things like, you know, ascites, you know, and a large liver. It's not a great liver, but or a baby in the way. Well, it's not a very good baby either, but you get the idea. All right. Those are things that the ventilator is going to have to push against. Or maybe there's a big mass in the belly, like a big tumor that needs to come out. Or maybe somebody hasn't had a bowel movement in such a long time that they're all impacted. All that stuff in there, the ventilator's got to push against it. That's going to go into our compliance measurement. Okay, now let's talk a little bit about airway resistance. Airway resistance, I like to use the term airway resistance. It's resistance to airflow. And to not use the word resistance in our definition, we're going to say that if air is trying to flow through something, a tube of some sort, it is anything that's going to impede or obstruct that airflow. And so we look at it in its simplest form. We have this tube. We're going to put flow of some kind through there. When gas flows through there, there are frictional forces, just like if I'm trying to move my hand across this board, it's harder than if I just did it through the air because there's frictional forces. Well, when gas or fluid is trying to move through this tube and come out the other side, there are frictional forces on the inside of that tube. And even if it's smooth, it's the same way. So if we have an input of 10, say there's a pressure of 10 and there's an output of 6, there's a difference of 4. So if there were no resistance at all, then it'd be 10 in, 10 out. But there's a little bit of a pressure or flow drop, however you want to talk about it, because of the resistance in there. And again, that's even in a smooth tube. And hopefully you're already picturing this as an airway or a blood vessel, because blood has flow going through it, and the lungs have flow going through it. Really, the heart and lungs, the circulatory system and the pulmonary system, they're very similar in so many ways. They are both pumps that move air or fluid through tubes. So you have resistance and compliance and all those things, all those basic physics principles are the same. So we have 10 in, 6 out. Let's say that we had 10 in and 3 out. These are just arbitrary numbers. That would mean there was more resistance in there. So let's apply that to the lung. So what can cause airway resistance? Well, if this is a cross-section of an airway, there is this smooth muscle that wraps around the airways, and if it gets too constricted, it's going to make the overall diameter smaller. And so that's going to make it, more resistance to flow going through. Just like if you put a straw in your mouth and try to breathe through it, you have to work harder to get the same flow because there's resistance of the small radius or diameter of that straw. Incidentally, cross-sectional area is the biggest determinant of airway resistance and vascular resistance. So that's bronchospasm. Well, let's put a little inflammation in there. Okay. Well, that makes it even smaller. And then we can put a little mucus in there. I don't think I have green, but just for the sake of a different color. There we go. A little mucus in there. And now you can see our cross-sectional area is way less. Now, things that affect resistance, those are the big ones. There's, mucus, inflammation, and bronchospasm are very significant ones. The three classic manifestations of obstructive disease are those. There's also down in the really tiny airways that have lost elasticity and are not supported by cartilage. They kind of get floppy, loss of elastance we think of as emphysema. And so when people exhale, those floppy airways are going to tend to collapse. And that's a natural thing. And it gets worse when they get short of breath and they're breathing more airflow, more collapse. And to demonstrate that, I have these two pieces of paper. Now, if I blow between these, you would think that they're going to blow apart because I'm blowing air in between. You think they're going to blow apart. But if I blow between them, see what they do at the end there? They collapse because they're not supported by anything. And that's how the small airways are that have lost their elasticity. They get real floppy. They don't have cartilage to support them because the cartilage is gone down there that low in the airways. And so that would be another form of airway resistance too that happens in the really small airways. By the way, that forward flow that creates that pulling in, that's Bernoulli's principle, if you remember that. Okay, there can be other forms of resistance, physical things like a tumor or a tooth that got aspirated or, whatever is down there. Now, we talked about resistance in terms of the radius or the cross-sectional area, and that's our biggest contributor. But Poiseuille's law tells us that there are several things that affect that. The length of the tube. So we think about things like an endotracheal tube that's really long. That can cause extra resistance. So we want to cut that off if that's your hospital protocol. If it's causing some problems and there's not a rule against that. There are some bad things about that. But if you cut that off a little bit shorter, then there's going to be less resistance. Probably the more common thing would be that's one advantage to trachs is that there's less resistance of that tube because it's a really small tube. Viscosity, which in Poiseuille's law is signified by an N, length is an L. So the more viscous a gas is, in other words, how thick it is, that's going to affect the resistance and how hard you have to work to pull that in, or how much pressure the ventilator has to take to push it in. So we think of things that affect viscosity. A really hot, humid day, the air is like a lot thicker. That's why they tell people with lung disease, make sure that you stay indoors because it's going to be harder to breathe. It's that thicker, more moist gas, a lot more humidity in there. On the flip side, a less viscous gas would be something like Heliox that they use for airway resistance, airway obstruction, to reduce the work of breathing because it's easier to pull that less viscous gas in there. And then, of course, there's radius, and we already talked about that. So those are the main things that affect airway resistance. And so before we go over to the ventilator, let me summarize this. And I'll talk about it again on the vent. But basically, when the ventilator is delivering that breath, or the spontaneously breathing patient or person is breathing in, the amount of work they have to do to pull air in, or the amount of pressure the ventilator has to use to push the gas in, is really a combination of compliance and resistance. How stiff is that lung? How much stuff is in the way that the vent's gonna have to push through. So we have the airway resistance is gonna be in the airways, it's resistance to airflow. And then we have the things that are gonna kind of pull in that the vent has to push against. And those were our three areas: the gas exchange units, the pleural space, chest wall, which includes things down here, remember, in the abdomen. So when the ventilator pushes that breath in, there's moving air. It's got to push through the airway resistance and the compliance, the stiffness of the lung. And so there's a couple of pressures on the ventilator, and I'll show you this when we go over there. But the peak inspiratory pressure, well, respiratory therapists, we typically call that the PIP. And that's going to be that peak pressure, the highest pressure that it took. That takes into account airway resistance and lung compliance. So the more resistance there is, the harder it's got to push. The less compliant the lung is, the harder it's got to push. And so we have this pressure of moving air, what it takes to fill it to the volume that we have set. And so that's our peak inspiratory pressure. Now, what if we were only interested in how stiff the lung is? In other words, I'm not really interested in airway resistance. I just want to know when that gas is in there without resistance, how hard is the lung pulling in? How stiff is that lung? And so to do that, remember, and this is key, remember that to have airway resistance, you have to have moving air because it's resistance to airflow. So you have to have moving air. Well, what if I could push that, say, 500 milliliters in there, using the example we did before? What if I push that 500 milliliters in there and before I let the patient exhale, I held that gas in there, let the air stop moving, and then took a snapshot of the pressure? That would be how much pressure it just took to hold the lung open without moving air. So it would be truly just compliance without resistance. Well, we can do that. It's called the plateau pressure, or sometimes we just call it the P-plat. Pressure plateau. So what that does is the breath will still go in. It'll still give you a pressure, the peak pressure readout, the peak inspiratory pressure, but it will hold that gas in there just for a brief second or so, and that allows air to stop moving. And remember, when air stops moving, there is no airway resistance. So air stops moving, and then it'll grab a snapshot. And now we have two different compliance formulas that we can use. We can use compliance, it's dynamic compliance. Dynamic means moving. And so that is the volume. And if we wanted to be real proper about it, it's the exhaled volume, not part of the explanations too much for this video, but it is exhaled volume. And then we're going to put that over the PIP, the peak inspiratory pressure, because remember, that has resistance in there. It's got moving air. It's the total pressure. So the dynamic compliance has resistance and compliance in it. I don't really take too much stock into that, because if I want to know resistance, I calculate resistance. If I want to know compliance, I calculate compliance. So to isolate just the compliance, how stiff the lung is without airway resistance, we are going to use the plateau. So still the tidal volume exhaled, only now we're going to put that over the P-plat. And that is without moving air. The air is not moving. So another word for kind of still or not moving would be static. So that is the static compliance. Okay? And so this is a true measure of compliance. Now, in order to interpret the numbers that we get, not really part of this talk, but I'll talk about it really briefly. To determine whether something's high or low, you have to have the normal ranges for it. And those vary depending on what source you use. So I typically use 70 to 100 milliliters per centimeter of water, and for static, and then 50 to 80 milliliters per centimeter of water would be normal. So again, those aren't set in stone. If you're in school, you should use whatever your instructor has told you to use, but should be somewhere around that. Static is always higher than dynamic because P-plat is always lower than PIP. Now, just for the sake of completing this formula, we do need to take out an elevated baseline, which would be a PEEP value. If you haven't learned that yet, that's later. But just to complete the formula, PEEP actually elevates the baseline, leaves some pressure in there after exhalation. We have to remove that from our formula, so on each of them. So if you want to know true compliance without resistance, that's the one you want to go with. Now, airway resistance, there's flow through here. So we have a beginning pressure and an end pressure and then flow through there. So for resistance, we're going to use the pressure difference, PIP minus P-plat, divided by flow. And flow is in liters per second. So let's do one of those, just for the sake of doing some math, because we did it for compliance. So let's say our PIP is 25 and our P-plat is 20. The difference there is 5. Remember, it's PIP minus P-plat. So that's, these are centimeters of water. So now we have a difference of 5 centimeters of water pressure and flow. Let's just say, just to make something mathematically easy, let's say the inspiratory flow is 60 liters a minute. All right. But the problem is with this formula, you need to make it in liters per second or it won't be correct. So 60 liters a minute is about, well, not about, it is 1 liter per second. So in this case, we just divide that out. There's no units that cancel, so you're just going to carry them through. 5 divided by 1 is 5, and that's 5 centimeters of water per liter per second of flow. In other words, for every unit of flow, that's how much pressure difference is generated. All right. Now, again, in order to interpret whether that's good or bad, we need to know what the normal value is. Again, depends on what source you read, or if you're in school, what your teacher uses is what you should use. But I use 1/2 to 2.5 centimeters of water per liter per second. And again, that may vary a little bit depending on what source you read. So that's a little elevated. Now, here's the interesting thing, and this is where it gets really useful in the ventilator, and I'll show you when we go over there. But because this is 1/2 to 2.5, so we could just kind of like always keep in our mind that, airway resistance is a couple. Just to ballpark it, right? 1/2 to 2.5, a couple of centimeters of water per liter per second. And if flow is somewhere around 60 liters a minute, which you're probably looking at usually somewhere between 40 to 60 liters a minute, which mathematically would make that a difference of 1 or 0.8 liters per second. It's almost the same no matter what the flow is. So really, the difference in PIP and P-plat is pretty much close to what your resistance is. So at the bedside, you can determine without even calculating airway resistance pretty close to what it is, even if it's not exact. So let's boil that down. Okay, let's say the PIP is 25, and the P plat is 23. And the flow is 60 liters a minute, which is going to be 1 liter per second. So my difference is 2. So we plug that into our formula for resistance. 25 minus 23 divided by 1. 25 minus 23 is 2. Divide that by 1, it's 2. And that's normal for airway resistance. So you can say that the difference between PIP and P plat is almost the same as airway resistance. Now what I was talking about before, let's say we go on the low end of flow, 40 liters a minute. If memory serves me right, I think that's somewhere around 0.8 liters per second. It doesn't really change our answer very much. It's insignificant. So you can ballpark whether you've got elevated resistance. And that's important at the bedside because when you have a patient who's got a high peak pressure, you're walking up, taking care of your ventilator, and pressures are going into the 40s or higher. That's concerning. And so you can grab a P plat and kind of determine whether that's a resistance problem, a compliance problem, or both, because they have different solutions. If it's a resistance problem, then we're going to start looking at, do they need a bronchodilator? Do they need suctioned? Things like that. Are they biting the tube? It's another cause. Lots of different things. Compliance issues are a little different. Maybe we need to think about changing the, if the lung is really stiff, non-compliant, then maybe we need to start thinking about changing our mode of ventilation to where we target pressure instead of volume. That's another day. There's another video on that too, by the way, on my YouTube channel. And just so you know, if you want to do math examples, math practice, I do have a math book out for its respiratory care math for students. Student-centered approach is what it's called. And there's lots of explanation for all this. Everything I've said is in writing, and it's there's practice problems with answers, and a lot of them have, if you got this wrong answer, here's what you did wrong. For resistance, students tend to forget to change this to liters per second. So, all right, so that kind of wraps up this part of it. And now we're going to go over to the ventilator and show you how all this works. Okay, so here we are at the ventilator, and we're going to show you all the things that we talked about on the board on the ventilator. All right, so if you're not familiar with ventilators, I'll just show you some really basic sections here so we all know what we're looking at. All ventilators have a section where things are set, and then they all have a section where things are what the patient's actually doing. So we are delivering 500 milliliters tidal volume, and just like we did on the board, and we're delivering that 10 times a minute, and that's our flow. We have it at 68 liters per minute. Could change that down to 60 for the sake of our math that we did before. And then we're just going to take our elevated baseline out of there. That's that PEEP I told you about. Okay, so right now I have it hooked to this test lung here, and there's no airways in there, so there's really no resistance that's of anything measurable. It's just a big spring-loaded bellows, but you can see it's going up there, and so the ventilator is pushing 500 milliliters into this. And here we go. This is our P peak right up here at the top on this upper left. And it's about 25, 26 centimeters of water. And so that, remember, is the pressure that it took to deliver the breath. It's pushing, it's using moving air, it's pushing through resistance, which is relatively non-existent here in this particular case. And it's also going against the compliance, which there's a spring on the side that would obviously make it, stiffer. We can adjust that here. Okay, so remember I said if you just wanted to isolate out compliance, we would need to grab a plateau pressure. Now this is a 980 ventilator by Covidian Puritan Bennett. And so I'm just gonna hit this lung button, and you can see it's got a picture of a lung with arrows in and a pause symbol. So that's an inspiratory pause. And so I'm gonna go ahead and start that. And it's gonna push gas in there, and then it's gonna read it. And there we go. Our P-plat is 25. And this one actually calculates the compliance for you, which is nice. But you can see the difference in our PIP, our peak inspiratory pressure, and our plateau is relatively the same. And that's because, again, there's no airways in here. There's probably a little bit of resistance at the connector, but it's negligible, so it's not really even measuring it. Now, if I were to make this test lung stiffer, that is, I'm just gonna make the spring a little tighter, and you'll be able to see the peak is gonna go up. Before it was like 26 or 25, and now it's up to 33. It's taking more pressure to deliver that volume. So our compliance will have decreased. It's accepting less gas per each unit of pressure, so it's stiffer, it's less compliant. And let's grab a P-plat. Now, I'm gonna give you a second to think. Do you think the P-plat's gonna stay the same, or is it gonna go up? Well, in other words, on a less compliant, stiffer lung, is it gonna take more pressure to hold that lung open? And hopefully you said yes. So let's go ahead and start that. And there we go. Our peak is 34, our P-plat is 33. So they both went up because it's a stiffer lung, but what did you notice? The difference stayed the same because there was no change in airway resistance, and there really isn't any. So what I'm gonna do now is I'm gonna put this tubing in here, and I've just stuffed it with some paper towels. We can agree that that would probably cause some resistance to airflow. There's stuff in the way there, right? So I'm gonna go ahead and put that in line here. Actually, first I'm gonna take this back to where it was. Try to get a peak of 25 again. Well, I didn't get it exact, but it's close. So we've got our peak of 23, and just for the sake of grabbing this again, so you can see there's still no resistance in there because I have not put this in line yet. So peak of 24, plateau of 23. Now, let's go ahead and add our resistance. All right, now that's in line. And now that ventilator is having to push through that resistance, so our peak should go up. Okay, so now I've got the resistance in there, and our peak, you can see, went up to 39.40 because it's having to push through all that resistance. But if we think about it, we want to, if we're interested in the compliance, how stiff the lung is, well, then we would grab a P-plat. And remember, the ventilator is going to push the breath in. We're going to have a higher peak because of that resistance. But our P-plat should stay the same because that resistance we added will not be factored in when there's no air moving. Because remember, resistance is resistance to airflow. So when the P-plat is being held, there's no airflow. You're just going to get that pressure that's used to hold that lung open, which is reflective of compliance. And so we hit that, and there we go. And P-plat's back at 24 where it was the first time. So when we have compliance issues, the P-plat and peak both go up together, and the difference does not change. When we have a resistance problem, the peak goes up, but the P-plat should stay the same because there's no moving air when we get the P-plat. Therefore, that resistance that made the extra peak is not a factor. Now, just as a note, sometimes you have both. Sometimes the P-plat goes up and the difference widens, and in that case, you would have both a worsening compliance problem, lungs getting stiffer, and a resistance problem both. So, hopefully that was helpful for you to apply compliance and resistance to a real situation.